paired electrons, and they are actually reactive species. The good point of that is that binding energy distributions are actually very important because it is better than action. So I am going to talk today about the use of atomistic simulations based on quantum mechanical methods. My talk was focused on showing the community the application of atomistic simulations based on quantum mechanical methods. The application of these methods in studying the chemistry in space, and in particular when processes occur on the surfaces of grains. So as most of you well know, grains are important ingredients in chemical reactions, in the evolution of the chemistry in space. And what we do with these atomistic simulations is to try to understand why the grains are important in this chemistry. And essentially, I normally mentioned that astrochemistry of the grain on grain surfaces is conventionally studied from the perspective of the observations, in which astronomers can know let's say the components that are in a given region, but they are not capable to know why these molecules are there, so the roots of the formation. Then another way to investigate astrochemistry of the grain surfaces is by making use of astrochemical models, which are also useful to rationalize the observations, but the key point is that in these models, the models have to introduce input parameters. Some of them are energetic parameters, and normally they are based on guess values, empirical estimates, and so they are associated with uncertainties in the way that the astrochemical predictions are also constrained to some uncertainties. And then a third approach is by means of experiments, in which an experimentalist, from a given set of reactant species, they obtained a set of products. But in the same way, they cannot know the mechanistic steps through which these molecules, these products are formed. And this is, well, we have done a lot of projects on that sense, but what is missing is an important part, at least for me, an important part, which is there is a lack of atomic scale information, which is very important, particularly in the interstellar medium, because due to the low conditions of temperature and densities, the elementary steps occurring on a grain surface, giving rise to chemistry, is essentially at a molecular level. So they are truly individual processes, and accordingly they resemble to molecular level. And by means of atomistic simulations, we can obtain these insights at a molecular level. And we can obtain also quantitative information like energetics, structures, dynamic effects. And so in my talk, I present the application of atomistic simulations in two particular problems in astrochemistry. One is on the formation of carbon-based molecules, the so-called interstellar complex organic molecules, and also another topic is on the carbonaceous materials. So related to the ICOMs, the interstellar complex organic molecules, the definition is that these are molecules between 6 and 13 atoms, in which at least one is carbon, and the other are heteroatoms like oxygen, nitrogen, sulfur, phosphorus. Okay, and they constitute about 40% of the molecules detected in the interstellar medium. And the key problem in the astrochemical community is how these ICOMs can form. And there is a prevailing mechanism, which is the radical-radical coupling. And this mechanism is based on the fact that we have ices covering particles. These ices are of volatile species, water, CO, CO2, ammonia, so on. And then ultraviolet photons impact on these ices in the way that they homolytically dissociate these molecules, forming HCO, NH2, CH3, etc. And then there is a moment in which we are moving from a cold region to a warmer region during the formation of a protostar. These radicals acquire mobility, can diffuse, and then encounter one to each other, forming the icon. For instance, let's take the case of formamide, NH2CHO. We have NH2 from one side, HCO from the other side. They diffuse and couple to form formamide, NH2CHO. That's great, but the problem is that when we do calculations in order to simulate these processes, we observe that these radical couplings present energy barriers, which initially was assumed that they are barrierless systems, because in the gas phase it's the case. You have a radical, another radical, and the reaction is driven by a spin-spin coupling. In the absence of the surface, they are barrierless, but on the surface they present a barrier. Why? This is because the radicals have interactions with surfaces, and in order to couple they have to overcome these interactions. In essence, what we have is a diffusion barrier, so we need the diffusion. Okay, and we calculated a set of radical couplings, and all of them present energy barriers, and this means that in ultra cold environments like dense molecular clouds, prestellar cores, this mechanism is not operative. So we have to look for alternative mechanisms, and I present two possibilities which have been postulated in the literature. One is the radical ice mechanism, and the other one is the three-body reactions. Let's start with the radical ice. This is that we have an ice surface and a radical lands on, and it reacts, this radical that is landing reacts with one of the components of the ice. Okay, and I show as an example the reactivity of CCH as a radical with water as a component of the ice. And we calculated the energy profiles, and we identified that indeed the reaction has a, let's say, the reaction is feasible in the way that if we calculate this coupling of the CCH with one water molecule in the gas phase, so in the absence of the ice, we have an energy barrier of about 100 kilojoules per mole. But when we have the ice surface, the reaction is almost barrierless. And the reason is because the coupling of the CCH with water, due to particularities of the electronic structure of the CCH as a radical, so there is a spontaneous formation of the chemical bond between the carbon and the oxygen. And then also because in the middle there is a proton transfer, and this proton transfer is not direct, but it is assisted by the water molecules of the ice. So in that case, water is acting as a reactant supplier. So water ice is acting as a reactant supplier because one icy water molecule is a reactant itself, and also it helps this proton transfer in the way that reduces the energy barriers, and they act as a chemical catalyst. Okay, this is for this kind of radical ice mechanisms, and then I also showed the three-body reactions. A three-body reactions is that, okay, we have one reaction first forming a radical, and this occurs in nearby the presence of a second radical, in the way that when we are forming the first radical, the reaction energy excess of this first reaction is used to overcome the barrier of the second reaction. Okay, something like clack, clack. Okay, and we show, we have simulated these processes in that particular case for the formation of acetaldehyde, CH3CHO, by means of the reaction. The first reaction is the hydrogenation of CO, so one hydrogen atom reacting with CO, forming HCO, and this reaction is close to a CH3, an already CH3, in the way that we have first the formation of HCO, and then the reaction energy excess is used to form CH3. And to investigate that, we perform what we call ab initio molecular dynamic simulations. This is a kind of technique in which we give energy to our system and leave the system to evolve by time. And what we did is, okay, we started the molecular dynamics in the formation of HCO, and then we leave the system to evolve. So we form HCO, and then we observe how the HCO and the CS3 approaches one to each other and form, and then there is a coupling in a barrierless way. So it's a proof that this kind of three-body reactions also are working in ultra-cold environments. This is related to the carbon-based volatiles, the formation of interstellar complex organic molecules, and then I finished my talk introducing a new research line in our group, which is based on simulations dedicated to carbonaceous materials. And in that case, I presented a way how to obtain atomistic models, structural atomistic models of carbonaceous materials, and then what we can do with these carbonaceous models. So the way how we model carbonaceous materials is that it's not innovative. It's recurrently used in atomistic modeling, and we have a diamond, which is a well-organized structure of carbon, and then on this structure we apply the high temperature in the way that we convert it like a liquid, in the way that we can disorganize the system, in the way that we have a completely amorphous carbonaceous material, and then we do a quenching, so we decrease the temperature, and we have a rigid system but amorphous. And then what we are interested in obtaining a cluster model. A cluster model is not a very extended system, it's just a portion of what we generated. And what I always usually say, to generate this cluster model, we take our virtual scissors and we cut around this amorphous system, this extended amorphous system, and we take only a piece of this material. And this is an amorphous carbon cluster, but then what we have to do is to hydrogenate, because in the space it is known that there is hydrogenated amorphous carbon, and we hydrogenate them by saturating all the dangling carbon bonds with hydrogen. And then this is one possible way to obtain hydrogenated amorphous carbon. And then let's move to the processing of this cluster carbonaceous material. And in our case, we are focused on collisions, grain-grain collisions, and in particular collisions between this carbonaceous material with silicates. And this is important because it is something that happens, or it is supposed to happen, in regions where we have grain-grain collisions, like in molecular outflow shocks, in which there are regions of the protostars, so in the protostellar envelopes, in the outside, on the outer parts of the protostellar envelopes, that there are jet streams of gas, of matter going towards the external regions in a supersonic way, in the way that you can have collisions. And also these kind of collisions are important in protoplanetary disks, in which you have grains and there is a collisions that where regions where the aggregation starts forming pebbles and ultimately planetesimals. Okay, so then we started to investigate these grain-grain collisions in the way that we have our carbonaceous cluster, and also with a silicate cluster. So in the past, in the group, we also have nanoclusters of silicates, and then what we do is to execute molecular dynamics, in which we have the collision between these two nanoclusters, and the point is to observe what is forming there. The first thing is that the clusters destroys, and what we have is fragments of these clusters, and some of these fragments are important because what we observe are CO, we observe formaldehyde, H2CO, we also observe silicon dioxide, seeds. So let's say we have to still analyze the results, we have to run more trajectories, but the point is that what we observe there is actually promising in the way in order to understand the grain-grain collisions and this kind of physical processing of grains. And that's it. This is what I presented in my talk. Okay, so thank you very much.